Good afternoon to all of you once again. Let us begin the class. Okay. We are in chapter 6 and the name of the chapter is Chemical Thermodynamics. Today is the seventh day of myself transacting the lesson to you all, Chemical Thermodynamics. It is a Friday. Now, as I have told you in the previous classes, I have talked about the different types of heats in the previous classes, like enthalpies during phase transitions, heat of fusion, heat of solution, okay, heat of vaporization, heat of sublimation, and heat of transition. Today, I would like to discuss with you all the next topic in this chapter, that is called Hess's law. Hess's law of constant heat summation. That is the next thing to be discussed in the chapter, and then we will finally complete this chapter. Okay. Now, how to state Hess's law? If there is a chemical change, if a chemical change can be made to take place in two or more different ways or steps, whether in one step or two or more steps, the amount of total heat change, it is same no matter by which method the change is brought about. So here look at this example. The example over here underneath. For the formation of carbon dioxide, it has been done by two methods. Okay. Now here in the first way, carbon burns in oxygen to give carbon dioxide. The enthalpy change for the reaction is minus 94.05 kilocalories. And in the second way, carbon is burning in oxygen to give carbon monoxide. This carbon monoxide is further burning in oxygen to give carbon dioxide. The individual enthalpy changes for the formation of carbon monoxide is given minus 26.42 kilocalories, and for the formation of carbon dioxide it is given minus 67.71 kilocalories. So if we add these two equations and cancel the unwanted things, then we get overall change. So if we add these two mathematically, we're getting 94 minus 94.13 kilocalories, which is almost similar to the step 1, and this is called Hess's law. Okay. Now, before proceeding to any other numericals, let us understand this Hess's law of constant heat summation properly. Remember, note that the heat of a reaction or the enthalpy change in chemical reaction depend upon initial state of reactants and final state of products, and it is independent of path which the reaction is brought about. So it is a path function, it is a state function. Remember, it is a state function. So for Hess's law of constant heat summation, it is a state function. Heat of reaction is same whether it is carried out in a single step or series of steps. So these are the two important points to remember before we proceed for the calculations involved in this topic of this chapter. Now, let us have a look at one illustration. Okay, let us take a reaction. A A can form B by step 1, and in this step 1, during the formation conversion of A to B, the enthalpy change is given delta H, and let us assume the value of delta H to be, say, minus Q calories, kilocalories, kilojoules, whatever. Now this A can be converted to B in another way also. First, you can convert A to C. This is step 1. You can convert A to C. Now when A is converted to C, then delta H1 is, you can take it to be Q1, small q1. Now this C can be converted to D. So here delta H2 is taken to be, it's assumed to be Q2, and then finally D is converted to B. So in this, delta H3 is equal to Q3. So this is path 3. This is path 1. This one is what? By path 1. And this one is path 2. In part 2, there are 3 steps. In path 1, there is only one step, single step. Okay, so according to Hess's law, delta H, this delta H is equal to delta H1 plus delta H2 plus delta H3. So we have assumed over here delta H1 is Q1, delta H2 is Q2, and delta H3 is Q3. So I hope you have understood the meaning of Hess's law of constant heat summation for a chemical change or a chemical reaction. Okay. Now, moving to one example on the next slide. Okay, have a look on the screen. Over here, we have taken the formation of carbon dioxide from carbon and oxygen, oxygen. So here, uh, let us take path one. Path one, okay, where carbon it is being burned in oxygen to give carbon dioxide gas. Now, for this formation of carbon dioxide gas, the enthalpy change delta H it is given over here. It is given here. It is given minus 393.5 kilojoules. So much of energy. That is path 1. It is occurring in a single step. Now, the other thing is here. The part 2, the path 2, it is also given. The part 2 is given where in the step 1 of part 2, carbon it is combining with oxygen to give carbon monoxide gas. So for this part 2 step 1, the enthalpy change it is given minus 110.5 kilojoules. And for part 2, now this carbon monoxide is now converted to carbon dioxide. So part 2 step 2, what is happening? The carbon monoxide is further combining with oxygen to produce carbon dioxide gas. Now for this part 2 step 2, the enthalpy change it is given minus 283.0 kilojoules. Now according to Hess's law, this delta H is equal to, you can say this is delta H1 H2, okay, or H, no problem, H1 H2. So according to Hess's law, this delta H should be equal to delta H1 plus H2. So if you try to add delta H1 plus delta H2 mathematically, then we will have minus 110.5 plus minus 283.0. If we add this, you'll get the answer kilojoules. 5 over here, 3 over here, 9 over here, 3. So it is coming to same, minus 393.5 kilojoules. So this is one illustration of the Hess's law. So by having a knowledge and concept of the Hess's law of constant heat summation, it is possible to find the overall enthalpy change for the formation of particular compound. Okay, I hope this is clear to all of you. Now moving to the next slide, Hess's law of heat summation. Look at this example. Now before the example, look at this sentence. The enthalpy change of an overall process is the sum of the enthalpy changes of its individual steps. Now in a single step, look at this problem. They're telling us calculate the energy involved in the oxidation of elemental sulfur to sulfur trioxide from reactions given below. So there are reactions given below. In the first step, we are converting sulfur to sulfur dioxide. The enthalpy change is minus 296.0 kilojoules. In the second step, this sulfur dioxide is converted to sulfur trioxide. The enthalpy change it is given minus 198.2 kilojoules. Now in the third equation, the elemental sulfur, is combining directly with oxygen to give sulfur trioxide. So they are telling us to find out the enthalpy change involved in the direct combination of sulfur to sulfur trioxide. So to get delta H3, to get delta H3, we have to simply add, delta H1 and H2. Delta H1 and H2. Have a look at the next slide over here. So here we can see on the next slide, sulfur plus oxygen, sulfur dioxide. Sulfur dioxide plus oxygen is sulfur trioxide. Now what they have done is, the first equation is multiplied by 2 and then they are added. This is cancelled out. Okay. And when you add them, you get sulfur trioxide. So if you add this to mathematically, minus 297 kilojoules into 2, okay, plus 198 kilojoules into minus 1. Okay, so we get total, we're getting minus 792 kilojoules. That is the answer for the question which you saw just now. Okay, so this is the application of Hess's law, how to get the values of the enthalpies of formation of a molecule. Okay, now this one you try it. Okay, you can try it just now. I am waiting for you all to copy the question. Take out the exercise copies. Okay, and copy the question. Example: the following equations are given for the corresponding delta H values for the formation of N2O nitrous oxide. It is given 164.1 kilojoules. For the formation of nitrogen dioxide, 180.5 kilojoules. Okay, all plus over here. And for the formation of nitrogen dioxide, it is given plus 66.4 kilojoules. Okay. Now they are saying, using these values, calculate delta H naught, for the reaction given below. So in this reaction, nitrous oxide is reacting with nitrogen dioxide to form nitrogen monoxide. So delta H naught you have to calculate. Okay, try this one. I am waiting. Okay, you do it. Yes, getting it, boys. Solve it. Solve it. Try it. Use common sense. You have to find the delta H naught for the reaction given below. Getting it?
Yes, sir.
Yeah. So what do you do?
Flip n to other side, sir.
Yeah, flip it.
So then we need to divide multiply by half,
Yeah.
sir.
So do the working.
So then the value of enthalpy will change. So that delta H naught will change.
Delta H naught will become how much?
So that will become minus 164.1 divided by 2.
Minus 164.1 divided by 2. Okay, let me check. So this is the equation whose N2O plus NO giving thrice NO. Equation is balanced. So we are supposed to find the delta H naught for this equation, no? Isn't it? Yes or
Yes,
no?
sir. Yes, sir.
Okay.
Yes, sir.
Now the values given over there is uh, the values given in the previous slide. Just check the enthalpy. The enthalpy for the formation of twice N2O, isn't it? It is plus 164.1. But here it is only one time, no? Will it be half of that? Will it be
Yes,
half?
sir.
So that is coming to how much? N2O.
So
So the
82.
delta H of the reformation of N2O, it is coming to 82.05 kilojoules. Okay. And similarly, delta H for the formation of NO. NO will be how much? Because twice NO is given 180.5. So here it is NO is three times, no? NO is three times. This one is sorry, this one is what do you call? Just check the equation. The equation NO2. Sorry, this is NO2. This is NO2. This is NO2. Okay, this one is NO2. So delta H F NO is given how much for the formation of NO? So this one has to be how much? Two times, no? This N2O is one time only, but delta HF for the formation of three molecules, no? Three molecules of NO should be how much do you get? Just calculate 90.25 into 3. 90.25 90.25 into 3.
So 270.75.
Yeah, 270.75. Correct. So this will come 270.75 kilojoules. Correct. Now, delta H for the formation of nitrogen dioxide now. Because there is only one mole, no? There is only one mole. So, nitrogen dioxide, 2 moles of nitrogen dioxide is 66.4. So, one has to be how much? Half of that, no? 33.2 kilojoules. Correct, no? Is it correct? Is
Yes,
it
sir.
correct? Okay. Now,
So we
now
need to change the sign on N.
over here, over here
So on N2O.
on N2O. Yeah, you can change the sign for N2. Yes. N2 it will be minus, no? Will it be minus?
Yes, sir.
Minus. And what about NO? That should also be minus. Hmm. Now, delta H for this reaction. Delta H not for this. What is the formula which I had given yesterday? Delta H to calculate the heat enthalpy of the reaction. I had given the formula yesterday. Let's go through it. Delta H not is equal to what? Reactant minus product or product minus reactant. Summation of, yes, summation of
Summation of.
H of product minus summation of H of reactant, no? R, isn't it? Now, for the product, over here product is 3 thrice NO, no? It is thrice NO, no? Correct. So 3 times NO, it is coming how much? Minus 270.75 minus of, open the bracket, reactants is where reactants is nitrous oxide and nitrogen dioxide. So it will be minus 82.05 plus 33.2. Simplify this, you will get delta H naught for this reaction. Simplify it. How much is it coming to? This will be 50, 49 point something, minus 49 point something, minus plus. So minus 270.75 plus 48, 49 point something. How much you get?
20, 220.9.
Minus,
Sort
minus no, 220
yes, sir. It's
point,
minus 270. Yes, sir. That's the value. Sorry.
220.9 kilojoules. That is the answer. That is the enthalpy of this reaction. Did you get that? Okay.
Yes, sir.
Okay. So this is one application. Okay, one numerical based on the sum which you have just now seen. Okay, I'll be doing some more numericals after this. Okay, so for this the answer is delta H is you're getting 220.9 kilojoules approximately. Okay. Now let's have a look at one more problem. Calculation of delta H enthalpy. Okay, look at this equation. This looks like propane. This looks like propane. Combustion of propane. Complete combustion. So propane, it is reacting with, it is burning in oxygen to give 3 molecules of carbon dioxide and 4 molecules of water. Now, just this is one step. No, now imagine that this reaction is occurring in 3 steps, which add up to the overall equation. So, in the first step, propane with graphite, it is being converted to graphite. It is giving hydrogen. Propane is heated to high temperature, delta H, positive. So it is absorbing heat. Plus sign is there, no? Endothermic. Then in the second step, this graphite, it is burnt to give carbon dioxide. Again, it is given out. And finally, hydrogen combined with oxygen to give water. So these are the 3 steps. Okay. Now in the formation of what? Carbon dioxide and water vapor. See, carbon dioxide is formed here, water vapor is formed over here. This will cancel. Okay, so imagine this above reaction is occurring in 3 steps, which add up the overall equation over here. Now, in this step, see, this is an summation. This is the Hess's law application illustration I'm giving. So delta H for this reaction will be, this is delta H1 plus delta H2 plus delta H3. Delta H1 का value is plus 103.85. Delta H2 का value is minus 1181 kilojoules and delta H3 is minus 1143 kilojoules. So if we add all these three, we will get the answer minus 2220 kilojoules. Okay, are you getting it? So this is the type of sums which you will get. Try to understand this. Okay, they'll give you the question like this: a reaction, the combustion of ethane, what you call propane, is happening according to the equation. Calculate its delta H naught or enthalpy change under standard conditions. Okay, and this equation will be given and these values will be given. Okay, so you'll have to simply write this formula and add this up directly and get the answer. So it is very easy, direct application of formula. Okay, so that is how we will apply Hess's law of constant heat summation. Okay, now moving to the next slide on the screen. One more question over here. There is a single step reaction. Calculate delta H for this reaction where carbon is combining with hydrogen to form ethyne. This is ethyne, C2H2 is ethyne. Given the following chemical changes, equations and the respective enthalpies have been given below. Now here, ethyne burns in oxygen to give carbon dioxide and water vapor. The enthalpy for this reaction is given. Again, carbon combines with oxygen to give carbon dioxide. Enthalpy is given. Again, hydrogen combines with oxygen to give water. Enthalpy is given. So they are telling us to find the enthalpy for this reaction of carbon and hydrogen. Okay, from by using these values, we have to get the value of the delta H for this first reaction, delta H. Now, what they have done, they have simply added. You see, the first equation, has been reversed. See, the first equation has been reversed. Watch carefully. If it is reversed, the negative sign goes away, it becomes positive, plus 1299.6 kilojoules. After that, the second equation remains as it is. The third equation remains as it is. And then they are added. The equations are added. Carbon is 2. Okay, others will cancel. This water will cancel. Okay, this will cancel. Hmm. Carbon dioxide will cancel. It will cancel. Okay, this oxygen, if we add 2 plus half, if we add 2 plus half over here, it will become 5 and 2. So this will also, I think, will cancel. Just check. Will cancel with this. Okay, and then we are now finally left with carbon combining with hydrogen. Two carbon atoms combining with hydrogen gas to give ethane. Only this much left. So we simply add all this. Plus 1299.6 kilojoules plus minus 787.0 kilojoules plus minus 285.8 kilojoules. So answer comes to positive value. It is an endothermic reaction. So the combination of carbon and hydrogen is an endothermic reaction. It results in the absorption of 226.8 kilojoules of heat energy. So that is the answer. Okay. So this is how we apply the Hess's law of constant heat summation. Okay. Now I will do some more examples to make the idea much more clearer. Okay. Now before doing the other examples, please remember some applications. Some applications I have to discuss. Application application of Hess's law. Hess's law. Now, the first application is like this. With the knowledge of Hess's law, it is possible to determine. It helps us to in the determination of heat of formation. With the help of the Hess's law, we can find the heat of formation, determine the heat of formation or calculate it. Okay, that is the first application. The second application is with the help of Hess's law, it is possible to determine. It helps in the determination of heat of transition. Heat of transition. That means transition from say allotropic forms, so rhombic sulfur being converted to monoclinic sulfur, monoclinic sulfur. Okay, the other forms orthorhombic, all those things possible. Okay. Now this is called determine heat of transition. The second one. The third one is it is possible to determine determination of heat of hydration. Heat of hydration. Now, what is heat of hydration? Let me explain you. Suppose if you take copper sulfate solid salt, and this copper sulfate solid salt you want to put in water, okay, and then crystallize it. So it is going to form crystals, okay, during its crystallization process. So the amount of heat which is involved, that is called heat of hydration. Okay. So here in the determination of heat of hydration, remember the enthalpy change involved in the conversion of 1 mole of an anhydrous salt into a specified hydrated form is called heat of hydration or enthalpy of hydration. So the direct measurement of heat of hydration is quite difficult, but it can be easily determined with the help of Hess's law. So by using Hess's law, we can possibly determine the heat of hydration indirectly from the given data. Okay, that is application number 3. Then we have application number 4. With the help of Hess's law, it can help us for the determination of heat of reaction, which you have seen just now over here. One previous numerical which I did, heat of reaction. Okay, so these are the various applications. These are the various applications for the what do you call calculation of determination of heat of formation, heat of transition, heat of hydration, and heat of reaction. So let us do one numerical. Okay, let us do one numerical and try to understand how we can apply the Hess's law. Okay, so one numerical. I'm going to write down the what do you call question. Okay, so the question is like this. Okay, calculate calculate the heat of formation of glucose from the data given below. From the data given below. Let me explain this question first. So the data given is like this. Carbon, solid carbon, it undergoes combustion, complete combustion to give carbon dioxide gas, and the enthalpy of the reaction, delta H, the enthalpy of reaction, that is heat of reaction, it is given minus 395.0 kilojoules. Okay. The next equation is hydrogen gas burning in oxygen gas. Okay. It is forming water after condensation, liquid water. So enthalpy of this reaction is given minus 269.4 kilojoules. And finally, we're talking about glucose, C6H12O6. In the solid state, it undergoes combustion. So I'm writing down the balanced equation. It is producing carbon dioxide gas and water, liquid state. And enthalpy of this reaction, it is given minus 2900 kilojoules. So this is the data given. Okay. Now, so they are telling us to find the heat of formation of glucose from all this. So this equation is combustion of glucose. No. So I think we can reverse this equation. If you reverse this equation and check whether they are balanced or not, this carbon dioxide, this first equation which you see, this is equation 1, this is equation 2. Okay. The first equation, it is carbon plus oxygen, it is forming carbon dioxide. So here, for the formation of glucose, we need elements like carbon combining with hydrogen, combining with oxygen to give what? Glucose, C6H12O6 in the solid state. So we are supposed to find the enthalpy of this reaction. Okay. Now, let us first balance this equation. Okay. So carbon is 6, so I'll put 6 over here. Hydrogen is 12, so I'll put 6 over here. Oxygen is 6, so I'll put 3 over here. Okay. Now what we'll do is, we know equation 1, 2 and this is equation 3. So what we'll do is multiply equation 1 by 6. Equation 1 is multiplied by 6. So multiplied by 6, equation 1. So I will get 6CS plus 6. Multiply equation 1 and equation 2. Both the equations you multiply by 6. Okay. So and add them up. 6 carbon plus 6 hydrogen plus, if you multiply by 6, equation 1 into 6 into half is 3. So we get 9. Sorry. It is 9. 9 oxygen. It will give us 6 CO2. I am adding directly. Okay. 6 CO2 plus 6 H2O. So equation 1 and 2 have been multiplied by 6 and then they are added, because this will be 6 CO2 and this will be 3 O2. 6 plus 3, that is coming to 9. Okay. So now what they have done is, for the enthalpy of this reaction, delta H, it is coming to 6 multiplied by minus 395.0 plus 6, the second one, this one, 6 into minus 269.4. Okay. So this is equation, let this be equation 4. Okay. This is equation 4. Okay. After that, subtract equation 3 from equation 4. So subtract equation 3 from equation 4. So if you subtract that, you will get delta H for the formation of glucose will be 6. We know already 6 minus 6 into, sorry, this is 6 into minus 395.0 plus 6 into minus 269.4 minus equation 3. So minus equation 3, the value is given, enthalpy is given minus 2900. Okay, negative sign because I have to subtract it. So upon simplification, I will get 3 minus 3986.4. This minus minus becomes plus, so plus over here 2900. So the heat of formation of glucose, if you subtract this, you get minus 1086.4 1086.4 kilojoules. 1086.4 will come zero point 0.4 kilojoules, which is the answer. So this is the heat of formation. Heat of formation of glucose. Okay, this is one example. Okay, by using the Hess's law of constant heat summation. Okay, this is one example. So this you can practice it. Okay, this sum you can practice it. Have a look at the working once again. This is the question. So from the question only make equations. The first equation, equation 1, the second equation is equation 2, and the third equation is equation 3. And then frame this equation. To form glucose, we need to add carbon plus hydrogen plus oxygen. We need to react carbon, hydrogen, oxygen and balance the equation. And then after that, we make equation 4. We make equation 4. When carbon, hydrogen, oxygen, they react, they will form carbon dioxide and water. So what we are doing is multiplying this equation by what you call multiplying equation 1 and 2 by 6 and adding them, we get this equation 4. And for this equation, we are getting the delta H for the formation of this reaction, that is equation 4. So it is coming to some value. Okay, it had come to around how much, minus 3986.4. After that, finally we subtract this equation 3 which we have obtained, that is equation 3, we subtract it from equation 4 to get the answer, that is the heat of formation of glucose. Okay, so this is one question. Now there are now only numericals left, to be solved from this chapter. Okay, so I will take one or two classes more from this chapter, and then I will do only numericals in this chapter, from this chapter, and then I'll try to complete this chapter, and then I'll proceed to the next chapter. That is, the next chapter for you all is which one? Tell me, which is left?
States of
States of
matter.
matter, gases and liquids, where we'll be learning about ideal gas equation, the gas laws, okay, numerical, Dalton's law, kinetic theory of gases. Okay, all these things we'll be learning in the next chapter. Okay, and that is the last chapter left for you all to do. Okay, because that chapter is also an important chapter, because we're dealing with the ideal gas equations. The pressure correction is there, the volume correction is there. Okay, the what do you call, the universal gas constant is there, along with the what do you call, kinetic theory of gases, the ideal behavior of gases, the non-ideal behavior of gases will be discussed in that chapter. Okay, so with this, I would like to end my class here only, but please hang on because I need to record your attendance also for today. Okay, so just hang on. Your attendance is recorded. Okay. Uh, Thank you so much, boys. Thank you so much. Have
Thank
a
you,
nice day.
sir.